Hi guys. Okay, so today we're going to start our new unit number 2 on organic chemistry. So I just wanted to take a minute and before we get into the actual lesson to remind you of how we're setting up these units, how the lessons of this unit are set up. So today we are covering lesson 5. And all this is found on that document called Welcome to SCH4U that I've shared with all of you. So the key questions for lesson number 5, today's question, are due this Sunday. Next week, on Monday and Wednesday, we'll be covering lessons 6 and 7, and each of those has its key questions. They're both due on Sunday, the October 10th. And then lesson number 8 on polymers is an independent study unit, meaning that I will share with you this lesson the same way I do my lessons here. And you guys can go over the material and understand it and study it. And the key question for lesson 8 is a bonus, meaning that you can hand it in, but you don't have to. If you hand it in, it will count as a bonus. And at the end, if you have handed in all of your key questions and you handed in all the bonus questions, for however many bonus questions you've handed in, I will look at your marks for all of your assignments and I can get rid of however many of your lowest marks that you've handed in bonus questions for. So, so I urge you, if you want to improve your marks and you want to, you can make use of these bonus questions, which then at the end will go towards possibly improving your marks. So altogether, there's 16 assignments that you have to hand in by the end of this term, and they make up for 40% of your final mark. And there's also a midterm test worth 30%, and then the final examination is also worth another 30%. So these 16 assignments, 4 of them we've already done, and then there is, in addition to the 16 assignments, I have 4 more bonus assignments coming up. So if you do your 16 assignments and you do your 4 bonus assignments, then I can go ahead and take off 4 of your lowest marks. If you don't hand these in, then I'm just gonna tally up your marks for the 16 assignments that you have handed in. Okay, and anyone that you haven't handed in, unfortunately, it would be a 0 for that assignment. Okay, so that is the setup for this course, the setup for this unit, and let's get started with our actual lesson. Okay, so this unit, first of all, is there any questions about what I just discussed about the assignments, the bonuses? Is everybody clear on that? Borna, Sasan, and Shadisa?
No question.
All good. Okay. If you have any questions, just email me and I'll answer your questions. So this second unit is about organic chemistry. And in this unit, we are covering carbon-based compounds. Essentially, all of the different life forms and the great diversity that we have on our planet, from all the different animals to birds to humans and plants, all of these organisms that are so very different, and yet they all have one thing in common, is that they are made of carbon-based compounds. And the science of studying carbon-based compounds in chemistry is called organic chemistry. And that is the focus of our unit here. And some of the basics I think you have covered in grade 11 chemistry. And we'll be talking about organic chemistry a little bit more in this unit. And we'll be talking about the different types of organic compounds. What are their practical uses, such as polymers and plastics? And the overall expectation at the end of this unit is for you to show an understanding of the structure of the various organic compounds and the chemical reactions that these compounds can participate in, We can investigate all the different organic compounds by talking about some experiments and research and predicting what are the products of some organic reactions that we can set up and name and represent the structures of these organic compounds using the IUPAC naming system and also molecular models. Finally, we will talk a little bit about the impact of these organic compounds on our standards of living and on the environment, on the ecosystem. So today's lesson number 5 on hydrocarbons. So as I mentioned, organic chemistry is the chemistry that deals with molecules containing elements carbon and hydrogen. So these organic compounds aren't just a part of living organisms, but they're also used as natural and synthetic polymers. And in this lesson, we will talk about these organic compounds, which we refer to as hydrocarbons. And these compounds are often used also in the petroleum industry. So at the end of this lesson, we will learn about the oil refinement process as well. Key concepts in today's lesson is to be able to describe some of the physical properties of the classes of organic compounds in terms of their solubility in different solvents, molecular polarity, their odor, melting points, etc. And to be able to use the appropriate scientific vocabulary to communicate these ideas that are related to organic chemistry. For example, the terms functional group and polymer. And the third key concept is to be able to demonstrate an understanding of the structure of these various organic compounds and of the chemical reactions that these compounds participate in, and to be able to predict the products of these organic reactions and name the structures of these compounds using the IUPAC system, and to be able to, again, evaluate these compounds in for our standard of living in these environments. So hydrocarbons. Hydrocarbons are the foundational molecules of organic chemistry. These are organic compounds that contain the elements carbon and hydrogen, as you may guess from their name, hydrocarbons. So they have hydrogen and carbon in their structure. So examples of some of these common organic compounds are molecules such as methane, SCH4, carbon and hydrogen, it's a hydrocarbon. Propane, C3H8, and butane, C4H10. These are all examples of the different hydrocarbons that we'll be studying. And these are the main components of many animals and plants, and they account for a wide variety of living organisms on our planet. And the properties of these hydrocarbons arises from the unique bonding nature of the element carbon. Now, if you recall from our lessons, our previous unit, carbon has the ability to form 4 covalent bonds with other carbon atoms and other elements. So if you recall, looking at the Bohr-Rutherford diagram here, for example, for a carbon atom, you can see that in its outer shell, in its valence shell, it has 4 electrons that can participate in bond formation. Or if you look at how we draw the Lewis structure for a carbon atom, it has 4. It's from the group 4 on the periodic table, so it's able to participate in 4 covalent bonds. And as such, it has the ability to form a great variety of shapes, from long chains to rings with single bonds or double bonds, or even triple bonds. Carbon is very, very versatile in that way. So let's talk about the term saturation when we're talking about hydrocarbons. Compounds that both contain these carbons and hydrogens are referred to as hydrocarbons. And when these hydrocarbons have no double bonds, as I can show you in these 2 examples of these 2 structures here, they are referred to as being saturated. saturated hydrocarbons. So saturated hydrocarbons contain only a single carbon-carbon bond. There are no double bonds here. When a hydrocarbon has got a double bond or even triple bonds, it's called unsaturated. And if you think about what the meaning of the word saturated actually means, saturated means when something has as much put into it as it takes, it's at saturation. When it's unsaturated, it means you can add more. So looking at the structure of these hydrocarbons, you can see there is no room for adding any more carbon-carbon bonds. They're all fully saturated. Whereas here, because of the double bonds or triple bonds, you could break these bonds and there's room for adding more carbons to these. These carbons are not fully saturated. There's room to add more, make more carbon-carbon bonds around these bonds if they're broken. So these are referred to as saturated hydrocarbons, where there is there's no double bonds, it's all single bonds. And here there's some double bonds and triple bonds referred to as unsaturated. So in hydrocarbons, you can also have isomerization, structural isomers. Isomers are compounds that have the same formula, so made up of the same number of carbons and the same number of hydrogens, but they are arranged to produce different structures, and as a result will have different properties. So one example of structural isoforms is the form 1-butene and 2-butene. So if you look at these, they're both butene, which means it has 4 carbons, 1, 2, 3, 4, 1, 2, 3, 4. So they both have 4 carbons, and they both have 1, 2, 3, 4, 5, 6, 7, 8 hydrogens, and same with this on this side. There's 4 on this half of it and 4 on this half. So notice that 1-butene and 2-butene are structurally different. The location of this double bond is different in the two structures, but both molecules have the same molecular formula. They're both C4H8. But when you use the IUPAC naming system, you name them differently. This is 1-butene because the double bond is located at the first carbon. This is 2-butene because the double bond is located at the second carbon. So these are structural isomers that have the same molecular formula, but their structures are different. Their atoms are arranged in a different way. The location of the double bond might be different in this case. So how do you name these hydrocarbons? For example, here on this previous slide, we saw that these two will have different names. One is called 1-butene, one is called 2-butene. How do you go about naming these hydrocarbons? So there's 3 classes of hydrocarbons based on how much, how their degree of saturation, how many bonds they have. So they can be aliphatic, aromatic, and then there's also derivatives. So the aliphatic hydrocarbons are referred to, in the case of single bond hydrocarbons, are referred to as alkanes. Double bonds are called alkenes, and triple bonds are referred to as alkynes. And we will learn more about these, and you will get used to these naming conventions as we go along in our lessons. Then you have what are called aromatic hydrocarbons. And these, the carbons form a ring-like structure, which is called a benzene ring. And these are aromatic hydrocarbons. And then on these, you can have on either the benzene or on the hydrocarbon chains of alkanes, alkenes, and alkynes, you can have functional groups such as alcohols, usually an OH group, esters, which tend to be scented compounds, and then amines, which are examples of amino acids, those building blocks that are found in protein chains. So we will get into the naming convention and how you name these hydrocarbons and what are the rules. And by the end of this lesson, we should have a good idea, following the rules, how to name really any hydrocarbon that's given to us. So first, let's talk about alkanes. So alkanes, as you remember, are saturated hydrocarbons. There's no double bonds. They contain only single covalent bonds. Alkanes are referred to as saturated, meaning that there's only single covalent bond between its carbon atoms. And their structure or structural formula in a condensed way can be written as, if you're writing the structural formula, I expect you to show every single bond. So if I ask you to write the structure, this is what I expect to see. If I ask you to write the condensed form, then you can short form it to read like this. And you can see, for example, here's a carbon bound to 1, 2, 3 hydrogens, so CH3. Then the next thing is a carbon bound to 2 hydrogens, CH2, another CH2, and finally it ends with a CH3. So this is a condensed way of showing this structures. So these alkanes, these organic compounds, are generally named using what is called the IUPAC system, which stands for the International Union of Pure and Applied Chemistry. And it's a method, it's a very systematic method for naming and drawing these organic compounds. This system uses prefixes, and these prefixes are based on how many carbon atoms the molecule contains. So this table has the prefixes for the first 10 alkanes. We can go through it. So if you have only, and the general formula is this CNH2, N plus 2, doesn't matter really. So if you have methane, so 1 carbon, a single carbon, it's called methane. The prefix is meth, and the ending is ane because it is an alkane with no double bonds. So if you have 2 carbons joined together by single bonds, then the prefix is eth, and this is an ethane. The ane part indicates alkane, which is a single covalent bond between the carbons. So all of these molecules will end in an ane, meaning that they have only single covalent bonds between the carbon atoms. You won't find any double bonds in these alkane molecules as signified by the ending ane in every single one of them. And then depending on how many carbon members there are here, the prefix is meth, eth, prop for 3, bute for 4, pent for 5, hex for 6, hept for 7, oct for 8 carbons, non for 9 carbons, and dec for 10 carbons. And as you do more of these types of questions and look at more of these examples, you will just get more well-versed, and you will just come to remember these prefixes of meth, eth, prop, bute, pent, hex, hept, oct, non, and dec. But for now, if it helps you, there is a little memory tip that helps you remember these prefixes all the way from 1 to 10 carbons. And that is goes something like Mary eats peanut butter pancakes happily, hugging our new dog. So the M should remind you of meth, eth, prop, bute, pent, hept, hex, oct, non, and dec. So if this memory aid helps you to remember these, that's great. Go ahead and use it. Otherwise, you just have to learn these prefixes for these these hydrocarbons. So then when you have an alkyl group is a branch of a molecule that's derived from an alkane. For example, you could have a methyl group, so the ending is YL. For example, a CH3 is a fragment of a methane molecule. So the methane molecule, if you remember, is a CH4. If we look back, CH4, that's in methane. So if you have something that has a methane, but it's added as a branch to a main chain hydrocarbon, then the ending instead of methane becomes methyl. So the methyl means it's a fragment of an alkane formed by removing a hydrogen. And we will use these, what are called alkyl groups. So the YL part is what we have in the names, il, methyl. So these are alkyl groups. And these are useful also when we're naming hydrocarbons. So again, following that same prefix rule of meth, eth, prop, but, pent, and so on, we can have methyl groups. So instead of methane, which was CH4, you remove one of the hydrogens just so that you could provide a bond to another part of the chain, and it becomes methyl, ethyl, propyl, butyl, pentyl, as opposed to methane, ethane, propane, butyl, pentane. So this is how you have alkyl groups. So when alkyl groups sometimes have 3 or more carbon atoms, then you can have isomers of these alkyl groups. And so then at that point, they might become attached to the parent chain at either end of their carbon atom or at the one in the middle, for example. So if you have 3 or more, so here is one way of showing it. So CH3, and then this is another CH2, and that's another CH2, and this R represents where the rest of that molecule is, whatever it may be. But the point being that this part is that alkyl group that is then added on to the parent chain. So the R represents the parent chain. So, so here, this molecule is called an isopropyl molecule, and it would be added, it can be added at any one of these hydrocarbons to the main parent chain, or it could be added at the end molecule. So depending on which arrangement of molecules we have, if you have 3 or more carbons, you may have different names. For example, if you look at a 4-carbon alkyl chain that might be added to the parent molecule here, so you could have 1, 2, 3, 4. You know right away this is a but because it has 4 carbons in it. And it's a butyl because you know it's a chain that's being added to the longer parent chain. And if it is added at one of the end carbon groups, it is referred to as N-butyl. You can also have isobutyl if it's arranged this way. You can also have S-butyl if it's arranged this way, and you can have T-butyl. So these are all isomers of propyl and butyl alkyl groups that you can have. And we will learn more about these and do some practices with naming these. And there's also a good section of it in your textbook if you want to read up some more and do some more of the questions that are in there. So we will definitely cover these more. And if there's any questions, please ask. So what are the IUPAC rules for naming alkanes? The first one is you have to identify what is the longest carbon chain. So it doesn't matter which way the structure is drawn. Try and see what is the longest carbon chain, and you start with that. So then after you've identified what is the longest string of carbons that you have, you start numbering the carbon atoms starting at the end that is closest to the branches, if there's any present. So you name each of the branches and then you identify its location on the parent chain by the number of the carbon at the point of attachment. And when you have more than one branch, then the branches are listed in alphabetical order. So these 4 are the rules. We will go through them very slowly and build on each of these concepts so that you can get used to the idea of how you go about naming these alkyl chains. Once you understand how to name them, then you can name any compound, and it's just a set of rules, a set of steps to follow. So let's look at this very basic example. Okay, so in this example, it's very easy. There's no branching coming off anywhere. It's just a straight chain of hydrocarbons. We count 1, 2, 3, 4, 5. So because it has 5 hydrocarbons, we know that we should have the prefix pent. Pent is for 5. Also, you might remember it from words like pentagon. Is a 5-sided figure. So pent is usually a very typical prefix for things that are 5s. So pent, and because we don't see any double bonds, it's all single bonds here between the carbons. So it must be a pentane. Okay. Let's look at another example. Here we count, and there is, we can see there's no double bonds, so we know it's an alkane molecule. It must have the ending ane. And then we count the carbons, 1, 2, 3, 4, 5, 6. 6 has the prefix hex. We put the 2 together. This one is called hexane. 6 carbons, no double bonds, all single bonds. A saturated hydrocarbon chain with 6 carbons in it is called a hexane. Okay. So far, these 2 are very straightforward and easy examples. So does everybody understand the concept of using these prefixes and then making sure that if there's no double bonds, then that the ending ends in an ane? Everybody clear? Borna, Shadisa, Sasan, everybody clear on that?
Yes.
Perfect. Okay. So now what if, instead of just having a very nice and easy straight chain, what if we had branches coming off of it? Then what do we do? Well, then we just, again, do exactly as we're supposed to. We follow the steps. What's the first thing you have to do? Let's look at this example here. Name the following hydrocarbon. Someone might ask you, how do you name this hydrocarbon? So locate the longest chain. That's the first thing you need to do, is count and see which one is the longest chain. Okay, so the longest chain maybe is this one. Let's count this one and see, is this our longest chain? Or maybe it's this one, and maybe that's our longest chain. Let's count and find out. 1, 2, and we're counting the carbons here, okay? 1, 2, 3, 4, 5, 6 carbons, if we choose this one as the longest chain. Or let's count this one. 1, 2, 3, 4, 5, 6, 7. Okay, 7. This is definitely the longest chain. So we should pick this as our longest chain and treat everything else as being side chains, as being alkyl groups that are then added to this parent chain. So right here, the 7-member hydrocarbon is our parent chain. So in this example, I put up this example to specifically caution you to be careful. Just because something is shown this way doesn't mean the straight chain is the longest chain, is the parent chain. No, you have to count and figure out which one is the parent chain. The longest string of carbons is always the parent chain. It might not be laid straight horizontally. It might be bent like that. That's fine, but that's the longest chain. So be careful here. So the parent chain is 7 carbons long. So the parent name has to have a hept in the beginning because it's 7, hept for 7. And then ane, because we don't see any double bonds, triple bonds. It's just single bonded carbon-carbon hydrocarbon chain. And then let's look at these side chains that I've circled in red, right? So this is the main parent chain, and in red, I've circled these side chains. So just let's take stock of what kind of side chains do we have. So we have a methyl group, which is a 1 carbon coming from methane, but because it's a side chain group, it's a methyl. So we have 1 methyl, and then we have 2, this is 1, and here's another. We have 2 ethyl groups, 2 carbons, so prefix has to be eth. And because they're alkyl side chains, branches, they'll have the ending -il. So we have 1 methyl, 2 ethyl side chains. Okay, so we know what are the side chains we've got. So here, let's number our parent chain. So we want to number it in a way, again, you have to choose which is the right end to number as carbon 1. So do you start numbering from this end? Is this going to be carbon 1? Or is this going to be carbon 1? Which is the correct way of doing it? You want to make sure that you number these in a way so it's either 1, 2, 3, 4, 5, 6, 7, or it's 1, 2, 3, 4, 5, 6, 7. Which way is it going to be? You have to choose the one that gives you the lowest number possible to your branches, to your alkyl groups. So what do I mean by that? I mean, if we pick this as carbon number 1, say we choose, okay, let's go this way, what happens? Then we know that we have our alkyl group, our our methyl group is on carbon number 2. And then this one is on carbon number 3. And then this one is on carbon number 4. So that it's it's 2, 3, 4. 2, 3, 4. Or if we number from that end, then 1, 2, 3. So this one would be on number 4, 5, and 6. So 2, 3, 4 will give us lower numbers than 4, 5, 6. So we choose this to be carbon number 1, because if we number it, it'll give us lower numbers. Then we go ahead and we list our alkyl groups in alphabetical order. So what were our alkyl groups? Our alkyl groups were methyls and ethyls. So alphabetically, E comes before M, right? If we look at the alphabet, A, B, C, D, E, F, G, E comes before M. So we want to name our ethyl first and then name our methyl, okay? Here in this case, we have 2 ethyls, right? We have 1, 2. So we give it the prefix diethyl, meaning we got 2 ethyls, and then we put which carbon they're on. So one of them is on carbon number 3, right? This is on carbon number 3. One of the ethyls is on carbon number 3, right there. And actually, I should have copied these and had them on this diagram too. Let's do that right now. Just gonna grab these and bring them down here. Okay. So one of them is on carbon number 3, the other one is on carbon number 4. So we call it 3,4 diethyl. And then we name our methyl, which is our next alphabetically. And where is the methyl? The methyl is on carbon number 2. So we write 2 methyl Okay, so up to now, all of this has been talking about all the alkyl groups. So we put those in the beginning, and then comes the parent chain name. Now the parent chain was 7 carbon long. It has no double bonds, so it is a heptane. So altogether, this molecule is called a 3,4 diethyl. One ethyl goes there, the other one goes there. 2-methyl, carbon number 2 gets a methyl right there. Heptane. These attached on these carbons of a 7-carbon alkane named heptane. Okay.
Miss, again, how do you count the ones inside?
So how do you count the ones that I've circled?
No, the ones that are in the side.
The ones that are on the side?
Yeah.
Okay, so which one? You mean this one?
Yes.
Okay, so this one, so remember, first thing you have to do is find which one is your parent chain. So the way to decide which one's your parent chain is you have to look for the longest hydrocarbon. So before we did any of that,
I got that part.
So we got the 7-carbon chain. So then everything else that you see is an alkyl group that is added on, is a side chain. It's like a branch, right? Right? So the rest of these are branches. Now, if you have 1 carbon, that is called a methyl because it comes from being a methane, but because it's a side chain, it's called methyl. So we name this, what kind of a side chain this is? This is a methyl side chain. Is that part clear?
Yeah.
Okay, so then let's look at some of these other side chains that are attached to the parent chain. How many carbons do we have?
2.
2. So when it's 2, let's look back at our, it's an ethyl, C2H5, right? Here is C2, 2 carbons, 5 hydrogens. This is an ethyl group. And so is this one. This one is also an ethyl group. So we see that on our parent chain, we have 1 methyl and 2 ethyl groups, okay?
Yeah.
And if you have 2 ethyl groups, you have to call them together diethyl, meaning that this molecule has got 2 ethyls, diethyl.
Okay.
So that's the diethyl part. But wait, we need to understand where are these ethyl and methyl groups located? Where on this parent chain are they? So we have to figure out which carbon are they on. So if we start numbering our parent carbon chain at this end, say if we say this is C1, this is C2, C3, C4. So then our first ethyl group is on C4, next one is on C5, next one is on C6, right?
Yeah.
Okay, so in that case, let me just jot this down and see. So we would have a 4, 5, right? 1, 2, 3, 4. On the 4th one, we have one of our ethyl groups. On the 5th one, we have another ethyl group. So it's a 4,5 diethyl. And then our methyl group is on number 6, right?
Yeah.
So you can name it like this, which would be the incorrect way of naming it. Or you could name it like this, which would be the correct way of naming it. You want to start putting the numbers at this end because how do you decide? Is this one the right way or is this one the right way? This is the right way because these numbers that are used, 2, 3, 4, are smaller numbers than 4, 5, 6. That's one of the considerations you have to take into account at the step where you're deciding which carbon is your carbon number 1. You're going to start numbering at this end or at this end. In this case, definitely at this end, because it will give you the numbers 3, 4, and 2, which are a smaller set of numbers than the numbers 4, 5, and 6. So if on a quiz, I show you these two names, 4,5-diethyl 6-methylheptane and 3,4-diethyl 2-methylheptane, and I say, which one is the correct name for this structure here? You will look at it and say, yeah, I can see how both of these could be correct, but this one is correct because it gives me the smaller numbers. It gives me 2, 3, 4, as opposed to 4, 5, 6. Is that clear, Shadissa?
Yes, thank you, Miss.
Okay, perfect. That was the big message here, is that this is not correct. You don't want to name it this way just because the numbers are a bigger set of numbers than the other one. Okay, so actually let's not do that. Somewhere down here, I've got a set of, aha, let me grab these because these are sometimes useful. Let's go back. So let's just say that this would be the correct naming convention, and this would be the incorrect one. Yeah, clear? Everybody clear with that one? Orna, Sasan, and Shadissa, are we all clear on why this one is correct and this one is incorrect?
Yes.
Yeah.
Yes.
Perfect. Okay, let's move on to our next slide. Okay, here's another example for naming a branched alkane. So if you are asked to name this kind of a compound, again, you just follow those steps that we talked about. So first step, what's our parent chain? What's the longest chain? So let's count it and find out which one's the longest. Is it 1, 2, 3, 4, 5, 6, 7, 8 carbons long? Or is it 1, 2, 3, 4, 5, 6, 7, 8 carbons long? So they're both 8 carbons long. Okay, so which way do we go? The root name is octane. So we want to identify what would be the one that will have, so what is attached essentially. So in this case, whether we go this way or this way, it's an octane. So we can choose either one as the parent chain. And the side chains, the alkyl groups, will be this one, a CH3, a methyl, or it could be this one. Not or, and it is this one. This one is a 1, 2, 3. Okay. So we number the parent chain from the end so that the substituents or the alkyl groups that are attached to the carbon atom have the lowest possible numbers. And if there's 2 or more groups and the numbering that we're doing is a tie, it can go either way, the group that comes first alphabetically would be the one to get the lowest number. So if we start numbering from the left, the numbering from the left gives the lowest number, 3 for the methyl group and 5 for the propyl group. So this is a propyl group. And if we start numbering from here, we get 1, 2, 3. So this will be on 3, For 5, this will be on 5, and then 6, 7, 8. Or if we start numbering from here, 1, 2, 3, 4, and then 5, 6. So we can either have our name have a 4 and a 6, or have a 3 and a 5. So 3 and 5 are lower numbers than 4 and 6. So we would choose probably going this way, but more importantly, the group that comes first alphabetically should get the lowest number. So which one comes first in the alphabet? F or prop? Anybody want to tell me alphabetically which one would come first? Ethyl or propyl? Would ethyl come first in the alphabetical order, or would propyl come first?
Ethyl.
Ethyl, thank you. Ethyl, because it starts with an E. E comes before P in the alphabet. So we want to make sure in this case that ethyl should get the lowest number. So numbering from this end, from the left, will give ethyl the lowest number, 3. For this, sorry, excuse me, why am I, I'm getting confused, excuse me, not ethyl, methyl. I think that's why there was such great silence from your end for so long. Not ethyl, methyl, excuse me, this is a methyl and a propyl. So which one comes first alphabetically, methyl or propyl? Methyl comes first because M comes before P alphabetically. So we start numbering from this end, that way our methyl, excuse me, I apologize for all that confusion. Our methyl will get the numbering up on the 3rd carbon, and our propyl will get the numbering 5. So, right, so here I've exclaimed that if the same substituent is present more than once, for example, if we have 2 of something, then you can write it as a di. So just that was the example that we had before. We had two of these ethyls, so that's why this was called a diethyl. We use the prefix di. And if you have 3 of them, you can use tri. If you have 4 of them, it would be tetra. And you would include the number of the carbons to indicate which carbon each of these substituent is located on. So if for example, if the methyl group is attached to carbons 3 and 6, then your prefix would be di, and it would be a 3,6 di, for example. This is not what we have here. But then, so finally, when you're writing this final name, you put the substituents in alphabetical order, ignoring any of the prefixes. So you don't think of the di as counting as an alphabetical order way of saying it. And you separate the words by hyphens, and you separate numbers by commas. So you use hyphens for words and commas for numbers. And in this case, we have a methyl group and we have a propyl group, and methyl comes before propyl in the alphabet. So the name should begin with the methyl part and then the propyl. And so it's a methyl propyl, not a propyl methyl. And then you have to say, where is that methyl? That methyl is on the 3rd carbon. So it's 3-methyl. And then 5-propyl, because the propyl is on the 5th carbon here. So the compound's name here is 3-methyl 5-propyl octane, because the parent chain 1, 2, 3, 4, 5, 6, 7, 8 has got 8 carbons. So, and then I just wanted to show you that sometimes you have structural formulas that are a little bit condensed, eliminating having too many bonds around the carbon atoms that don't have any substituent groups. And if you have this kind of an arrangement, it just takes less space and makes it easier for you to see the substituent groups. For example, if we look at this example here, you can see in this butane, you have a methyl group here and a methyl group here, and it's a butane. So 1, 2, 3, 4 with 2 methyl side chains. So it's a 2,3 dimethyl butane compound. Or for example, in this one, you have 1, 2, 3, 4 is your parent chain. It's a butane. And you have 2 methyl groups, both of them on carbon number 2. So it's a dimethyl butane. And where are those? Those dimethyls are on both on carbon number 2. So you would write them as 2, 2 dimethyl butane. Okay. So these two, if you notice, are actually structural isomers, right? They both have 2 methyl groups on a butane chain, but the location and the arrangement of the methyl groups are different. And so the numbering system in the name helps us realize that for this name, we would have this type of structure. And for that name, we would have that type of structure, okay? So really just going through more examples is the way to understand naming, is just to see enough examples. So I'll do like 2 more examples, I think, on this topic. And then we're going to talk a little bit about the properties of alkenes. So let's look at another example of how you would name branched alkanes. So again, first step is, everybody can say it with me, identify the parent chain. That's our first thing to do. So first thing you do, be like a detective, go and see which one of these chains that you count will give you the longest number. Will it be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10? Or will it be 1, 2, 3, 4, 5, 6, 7, 8, 9? Nope, definitely not this one. It looks like this one will give us the longer chain. So we choose this to be our parent chain. So we know that this is our parent chain, and we treat everything else as substituents that are attached to the parent chain. So we identified that our longest carbon chain has 10 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And if it has 10 carbons and no double bonds, this alkane is called a decane. Because of its 10 carbons, it gets the prefix dec, and it's all saturated. There's no double bonds here. It's called an ane, decane. So then we want to, now that we know which one is our parent chain and what it is, it's a decane, everything else is a substituent. Let's identify what are these other groups, these substituents that are attached to the parent chain. And this carbon compound has got a 1 carbon group. There it is. There's 1 carbon here. A 1 carbon group. A 1 carbon group is called a methyl. It has a 4 carbon group. See, 1, 2, 3, 4. This is a 4 carbon group here. A 4 carbon group is called a butyl, okay? And we will look at which kind of a butyl isomer it is, because butyl can have different types depending on if the CH3 is here, or if it's just one straight long chain of 4 carbons here. So we know that it's got a 4-carbon group, a but of some type, a butyl of some type, and it has a 2-carbon group. So this is the 2-carbon group. It's in 2-carbon groups are called ethyls. Okay. So we identify in step 2, we identify, so what are these attached groups on our parent chain? Then in the 3rd step, we number our parent chain from the end in such a way that the substituents, these ones that I've circled in green, would get attached to the carbon atom with the lowest number, okay? And if there are 2 or more groups and the numbering is a tie, then the group that comes first alphabetically is the one that should get the lowest number. That's the numbering system that we choose. So numbering from either end, from this end or that end, places the first group on carbon number 3. What do I mean by that? So if we count from here, if we say, okay, this is, maybe we want to call this end carbon number 1. 1, 2, 3. Oh, so methyl comes at carbon 3. But what if we go from this end? 1, 2, 3. Oh, then ethyl becomes at carbon number 3. Which way do we go? So either way we go, our first group is at carbon 3. But since ethyl starts with an E and methyl starts with an M, so E comes before M alphabetically. So the number from the ethyl end of the molecule is the one that we use, okay, using the blue numbers. So we want to choose 1, 2, 3. So that we can number it either way, either this way or this way. But which one is the correct way? Here, using the blue numbers is the correct way, not the red numbers. The red numbers will give you methyl on carbon number 3, but we prefer ethyl be on carbon number 3 because ethyl alphabetically comes before methyl. So this makes the ethyl group on carbon number 3 the butan 2-il group on carbon number 6, right? Here, carbon number 6 gets that group. And the methyl group then comes on carbon number 8. And of course, recall that if the same substituent is present more than once, use di, tri, and tetra in front of it, and then include a number to indicate where the location is, which carbon this is located on. And then in step 5, you write down the final name, listing your substituents in the alphabetical order now, so that you have butan 2-il, you have ethyl, and you have methyl. So it would be a 6 butan 2-il, you would write this one first. Then alphabetically E would come next, so you would write your 3-ethyl, and then finally your 8-methyl. And then finally it would be a decane. Or another way to write this, and we will go through these. This can be written as a 2-butan 2-il, or an S-butyl is another way of saying this. You can write 6 S-butyl, 3-ethyl, 8-methyl, decane. Okay, so there's a lot here, but if you just go through this step by step on your own time, slowly, you should be able to understand step by step how you arrived at this. And as far as this butan 2-il or S-butyl, just refer to the table that talks about the different isomers of butyl. So you could have S-butyl, or another way of naming this was the 2-butan-il, was S-butyl, T-butyl, isobutyl, and N-butyl are perfectly acceptable ways of writing this. One more example. In this example, we're talking about cyclic alkanes. So if the parent carbon is attached in a carbon ring, the longest carbon chain is in a ring, okay? So in this case, we have 1, 2, 3, 4, 5, 6 carbons. So it is called a cyclo, meaning a ring. Hex, meaning it's a 6-member carbon ring. Ane, meaning no double bonds, only single bonds. So this is a cyclohexane. And then we want to identify all the groups that are attached to this parent cyclohexane. So where are the groups? It has one CH3 here and another CH3 here. So both of these are methyl groups. Then we have to decide, okay, on this ring, where does our numbering start? Our numbering starts at which carbon? Again, you want to do your numbering in a way to give your two groups the lowest numbers. And if there are two or more groups and the numbering is a tie, the group that comes first alphabetically gets the lowest number. In this case, the two groups are identical. They're both a methyl, so we don't need to worry about which comes alphabetically first. And so we can start our numbering either at this one or on this one. Either way, we can go 1, 2, 3, 4, 5, 6, or we can go 1, 2, 3, 4, 5, 6. Either way is correct because either way will give you the same answer, a 1 and a 3. And on a ring, if you only have one substituent, so suppose you didn't have this one here, you only had one, and if it's a cyclane, you don't have to even, you can, but you don't even have to indicate that it's located on carbon number 1, because it's intuitively understood that if you have just one substituent, one group, well, then that has to be designated carbon number 1. The carbon that it's attached to will have to be designated carbon number 1. That's what this note means here, that if you don't have to include number 1, if only one substituent is present on the ring, because by definition, that would be carbon number 1, by definition of the IUPAC convention. In step 4, if the same substituent is present more than once, such as is the case in our example here, if it's present more than once, use the prefix to indicate this. So give it a di or a tri or a tetra. In this case, we have, what do we have? We have 2 of these methyl groups. So it becomes dimethyl. And then you have to give numbers to say, where are these dimethyls located? Well, they're located at carbon 1 and carbon 3. So then you want to write the name, listing the substituents in alphabetical order, ignoring prefixes. So when you're picking, in this case, you only have methyl groups, it's a dimethyl group, but suppose you had more other, you had methyls, you had ethyls, you had propyls, whatever. You want to list those in alphabetical order, not paying attention to the di part. So the D doesn't count in your alphabetical consideration here. For example, the M would, okay? So the name of this compound would then be a 1,3 dimethyl, right? It's dimethyl because it has 2 methyl groups. Where are those methyl groups? They're on at 1 and 3. And the parent chain that they're attached to is a cyclo. We're using the word cyclo to indicate that it's cyclic, it's a ring. They're attached in a ring, in a carbon ring arrangement, and that it's a hexane. There's 6 of these carbons attached together, and it's an ane. no double bonds, all single. So that's how you would name this structure. If you're shown this and asked to name it, these are the steps you follow. Now, if you're given the name of an alkane, if you're given the name and asked to now draw the structure, follow these steps. First, you draw the parent chain or the parent carbon ring from the last part of the name. So the cyclohexane part, or if you look at the other examples we used from the decane part. So you would write your parent, you would draw the structure of your parent chain or parent carbon ring first. Then you would look and see what are the substituents and where are they attached. And then you would draw the substituents and attach it to the correct point on the parent chain or the ring. So kind of working in reverse. All right. Was this slide, this example of how to name cyclic alkanes clear for everybody? Is there anything here that really confused somebody? I'm happy to clarify things right now. Orna, Sasan, Shadisa, all good?
I'm good.
Perfect.
Me too, miss.
Yeah.
Awesome.
Thanks.
Okay, good. So let's talk about some of the properties of, let's see how many more slides. Some of the properties of these kinds of alkanes, the physical properties and chemical properties of these alkanes, because the carbons and the hydrogens on alkanes have pretty similar electronegativities. They don't have huge difference in electronegativities. Alkane molecules are essentially non-polar. So if you look back on our the lesson where we talked about the electronegativity of molecules, there's not a huge difference. If you look at the difference, the delta electronegativity of the two atoms, hydrogen and carbon, it's not huge, and it makes them fall under the category of non-polar molecules. And in non-polar molecules, you have London dispersion forces acting, correct? If you recall from our previous unit. And London dispersion forces, well, you get more London dispersion forces as you have more atoms. So essentially, the longer your carbon chain, the bigger number of dispersion forces you have. So a short hydrocarbon chain won't have as many intermolecular forces as a longer hydrocarbon chain. So London dispersion forces increase as the number of carbons increases. And when London dispersion forces increase, that means properties such as boiling point also increase, because that means stronger intermolecular bonds, so higher boiling point as the number of carbons increase in the molecules. These molecules also have fairly low density, and most of them are less dense than water and are not soluble in water, and they will tend to float. So most hydrocarbons will not be soluble in water, have lower density in water, and will float. If you try to mix them with water, these would be more oily substances. And some of the chemical properties of these alkanes is that generally these alkanes have very low chemical reactivity. Nothing really exciting going on in them, just carbons and hydrogens. Generally low reactivity except for combustion. Combustion reactions are the most important chemical reactions that alkanes have, because these combustion reactions are very exothermic. I don't know if you remember this term from your previous chemistry course. Exothermic means producing lots of energy, giving out lots of energy. And alkanes are very important fuel chemicals. So things like butane that we use to burn the combustion reaction of butane with oxygen is represented, for example, over here. You have butane, you have oxygen, and when you have a combustion reaction, they are fully converted to carbon dioxide gas, some water vapor, and lots of thermal energy. And the other chemical property of these alkanes is that they participate in substitution reactions with halogen compounds such as Cl2, this chlorine, to produce alkyl halides. And these types of reactions we will talk about in one of the following lessons coming up in this unit. So if you have these alkyl halides, where you have these halogen groups such as chlorine attached to it, how do you name them? So alkyl halides are written by writing the root of the halogen name first, then with the suffix O, followed by the name of the parent alkane. So that is how you do it. So for example, if here we have some bromines attached to this alkane group, then it becomes a bro, use the root of the halogen name first, so bromo, use the suffix O. Or if it was chlorine, it would be chloro. So in this case, you would use the suffix bromo, and you can see that it's attached to 1, 2, 3, 4, 5 carbon chain. 5 carbon chain is a pentane here. So it would be, and there's 2 of them. So it would be a dibromopentane. And we need to indicate where these di-2 bromos are located. Where are these 2 bromos located? This dibromo is on what part of this pentane? It's attached to which carbons? So we need to number our carbons and indicate which number there are. So you want to number the carbons of the parent chain beginning at the end that is closest to the first substituent, whether it's an alkyl chain or a halogen. So whether this was a bromo or if this was maybe a methyl or something, you want to start it beginning at the end nearer to the first substituent. And you want to assign each substituent a number according to its position on the chain. So if there's substituents that are present from the same distance from both ends, so suppose it was in a way that it didn't matter whether you numbered from this end or started numbering from this end, either way, they would be starting with the same number. Then you want to choose beginning at the numbering at the end that is closer to the substituent with the alphabetical priority like before. So for example, if you had a bromo, and then if you had a, let's say a methyl, well, B comes before M. If both of them were, say, at number 2, both of them were at a carbon, that would be number 2. So you had 1 here and 1 here, and whether you count from this end, your methyl might be here, and at this end, your bromo might be here. So either way, counting from this end, this would be carbon number 2. Counting from this end, this would be carbon number 2. Then you would choose the end that had the bromo on it, because alphabetically it gets priority. And so you would count numbers from that end. In this case, we only have bromos. We have 2 of them. Let's start counting from the end. That will give us 1, 2, 3, 4, 5. So 1,3-dibromopentane would be the name of this alkyl halide, as opposed to if we were to number it from this end, it would be incorrect numbering because it would be 1, 2, 3, 4, 5. So 3,5-dibromopentane would be the incorrect name for this structure. 1,3-dibromopentane is the correct naming convention. Some of the properties of these alkyl halides is that these halogens are chemically related to the elements that they come from, such as fluorine, chlorine, bromine, iodine, and astatine. Halogens are generally much more electronegative than carbons and hydrogen. If you remember, these set of elements occupy the top right area of the periodic table. That's where most of the more electronegative elements lie. And so they are more electronegative and they tend to attract electrons. That's what electronegative means. It means that you have a pull on the electrons, pulling them away from the carbon atoms on the rest of the chain. And so these molecules that have these halides tend to be polar molecules. So this end of this molecule, for example, will have more of a negative dipole on it than this end. This one would be the more positive end, and this one would be the more negative end, where the electronegative atoms are pulling electrons from the rest of the chain. These would be polar molecules. And this resulting polarity increases the strength of intermolecular forces, if you remember, since more energy is needed to overcome these types of forces. And so the boiling and the melting points of these alkyl halides are higher than those of the corresponding alkanes. So a pentane group, if you were to compare this dibromopentane to just a straight pentane with no bromines on it, the melting point and boiling point of the bromopentane would be a lot higher than the corresponding pentane as a result of its polarity and as a result of its increased strength in intermolecular forces. Okay, so that covers our section about the saturated hydrocarbons, the alkanes. Now we can also have unsaturated hydrocarbons, or alkenes and alkynes are the two unsaturated hydrocarbons that we can have. So the method for naming alkenes and alkynes, as you may guess, is very similar to the method for naming alkanes, except that the carbon chain chosen as the main chain must contain the double or the triple bond, even if it's not the longest chain. So in this case, if you see double bonds or triple bonds, that has to be part of your main chain, that area of the molecule. Don't choose it as the side chain, use it as the main chain. And that would make your ending of that molecule -ene in the case of a double bond, or -ine in the case of a triple bond. So for example, you would have methene, ethene, propene, butene, if you had double bonds, or -ine, such as methine, ethine, propine, butine, pentyne, hexyne for triple bonds. So the IUPAC rules for naming alkenes and alkynes is, number one is you have to identify the longest continuous chain of carbons containing the double or triple bond and assign the base name. The main chain must contain the double or triple bond, even though it may not be the longest chain. That's very important. That's your first step. Your second step is to number the main chain, beginning at the end, which will give you the lowest possible number for the double or triple bond. So if you choose the end, that will give the lowest number to the carbon that has a double or a triple bond. So for example, if the double bond is between carbons 3 and 4, use the lower number 3. Let's look at this example here and name this molecule. So here we see our double bond, so we know this has to be part of the main chain. In this case, there are no substituents, no other alkyl groups attached. It's pretty straightforward. This is our main chain. It has how many? It has 1, 2, 3, 4 carbons, making it a bute. It has a double bond, making it a butene molecule. And in this case, where is the double bond? The double bond is located at carbon number 1. This has to be carbon number 1. We can't choose this to be carbon number 1 because then that would make it 1, 2, 3, 4. Then our carbon bond will fall between carbon 3, will fall on carbon 3, and that's not the correct naming convention. Remember, you have to start at the end. That will result in the lowest number for the double or triple bond. So you have to choose this to be carbon number 1 because that's where the double bond is. So you would choose this as carbon number 1, 2, 3, and 4. And since this hydrocarbon has 4 carbons, it's a butene. And in this case, you can either call it a 1-butene, making sure we fully understand that our double bond is located at carbon 1. Or in this case, if you see just the name butene, you know that that means that the double bond is on carbon number 1, because if it was anywhere else, they would have to give you the number. Is it on 2-butene? You would have to say it's on 2-butene. But if you just see butene, that means on carbon number 1, between carbon number 1 and 2. And if you see 2-butene, then that means that the carbon bond is between the second and the third of the butene here in this case. One more example, name the following molecule. Okay, start off by numbering your carbon chain, giving the lowest number possible to the triple bond. So 1, 2, 3, 4, 5, 6. If we start numbering at this end, or if we start numbering at this end, 1, 2, 3, 4, 5, 6. So in this case, it's a very symmetric molecule. It doesn't matter which way we start numbering. Either way, the triple bond falls on carbon number 3. And then we know that it's a 1, 2, 3, 4, 5, 6, 6 carbons in this molecule, and it has a triple bond. So it becomes, and the triple bond is on carbon number 3, so it becomes a 3, indicating the position of the triple bond. Hex, indicating that it's 6 carbons. Ine, indicating that it has a triple bond on its third carbon in a 6 carbon alkyne chain. Okay. So were these 2 slides for alkenes and alkynes clear for everybody? Borna, Sasan, and Shadisa?
Yes.
Perfect. Okay.
Yes, ma'am.
Yeah, great. Okay. Now, as you go along and practice with your support questions, if you find that anything is confusing, just feel free to ask. You can email me, or you can ask to talk about it before class or after class. You don't have to necessarily wait until our end of the unit review. You can clarify it much earlier than that if you have any questions. So then aromatic hydrocarbons. So the benzene ring, and this is shown like this, is considered the parent molecule for all aromatic hydrocarbons. And the name of the base name is benzene. When you have a 6-membered cyclic chain with these double bonds here between its carbon atoms. And when you're naming structures that have a benzene ring, whether it has various substituents, whether it be alkyl groups or halide groups, the same rules apply in numbering the carbons. However, you have to make sure that the longest carbon alkyl group side chain will become carbon number 1. And you don't need to number the alkyl group if there's only just one of it, right? If there's one, it doesn't matter if it's here or here or here. It's all the same if there's just one. That one will be on carbon number 1. So if you get an example of this following molecule and you're asked to name it, you can see right away that the base name has to be benzene. You see that you recognize right away the benzene ring, the benzene molecule. So you know the base name is benzene. And then you realize that you have 2 chlorine atoms attached, 1 and 2. And the naming convention for adding these halogen groups is you start with the name of the halogen. In this case, it's a chlorine, and then you add O at the end. So it becomes chloro, the O at the end, chloro. If it was bromine, bromo. If it was fluorine, it would be fluoro. And then in this case, we've got 2 of them. So we need to add the prefix di to indicate that we've got 2 chloro groups on this benzene ring. And where are they located? Well, we need to number them in a way that they always get the smallest number. So it would be incorrect to start numbering at any of these other carbons as carbon number 1, because that would give higher numbers to these carbons with the chlorines on them. So you pick one of these and it becomes either 1, 2, or it becomes 1, 2, either way, it's 1, 2 dichlorobenzene. One more example with benzene, name the following molecule. Again, we look at it and we see right away, we have our benzene ring. That's our main group. So our parent group. So we know benzene would be the ending of the molecule. It's a benzene type of molecule, and then it has some attachments on it. Let's identify those attachments. Well, we've got a couple of chlorines, 2 of them, so we know it's got to be a dichloro. And then we have a 1, 2, 3 carbon chain attachment. A 3-carbon alkyl would be called a propyl, right? It would be a propyl. So it would be some sort of a benzene, some sort of a dichloro in front of it, and propyl. And then let's figure out which would be the way to number this. How do we choose that propyl should be at carbon number 1? Well, remember when we were looking at the rules for numbering the benzene ring is that the longest carbon alkyl group side chain will become the first carbon. So if you have alkyl groups and if you have halogens, this one takes precedence over the halogens. The longest alkyl side chain group will get carbon number 1 designation. So this becomes carbon number 1, 2, 3, 4, or 1, 2, 3, 4, 5. So yeah, you don't want to do your numbering in this direction because then these 2 will be 4, 5. If you go this way, there'll be 3, 4. That's the correct way of doing the numbering here. So it becomes a 1 propyl and 3, 4 dichlorobenzene. Okay. So that's how you would name that one. Sometimes if the benzene ring is considered a chain rather than the parent, for example, if really you can see that maybe this is the longer, if you choose this to be the parent chain, then the benzene becomes a branch rather than the parent. Sometimes this is also correct. And in this case, this will be called a 2-phenyl. And the benzene ring, when it's referred to as a substituent or as a group that's added on, is given the name phenyl. So that's a benzene ring, that's an attachment, that's a substituent, is a phenyl. So in this case, the parent chain is this butane. So you can name this molecule two ways, and both ways would be correct. It can either be a 2, as you can call it carbon 1, 2, 3, 4. On the 2, you have your phenyl, so it can either be your 2-phenyl butane, that's the butane being the parent chain, or you can look at this and say, okay, this is my parent here, the benzene, and in that case, it's an S-butyl on carbon number 1. It's an S-butyl benzene. Both of these would be correct. There are some support questions for you guys to practice with. I really encourage you to do that. And finally, we talked about how a lot of these hydrocarbons were very important sources of fuel. So we need to talk a little bit about how these hydrocarbons are obtained, how are they purified, and a process called fractional distillation, where petroleum or crude oil, which is really a thick, dark liquid mixture of different hydrocarbons of different length, different molecular size and composition, depending on where it's mined from, where this petroleum is, this crude oil is from. And you can't use this crude petroleum oil as fuel directly. It must be further refined or fractionated, separated into its different, separated by its properties, by its length of hydrocarbon chains, and then you have different uses for them. You get a separation of carbon chains that are 1 to 4 carbon chains long, and these are typically are fuel gases such as methane and ethane and propane and butane. These are all our petroleum gases. Then you can get our C5 to C9s, which lead to our naphtha chemicals. You get gasoline or petrol, which are typically C5 to C10 carbon chains. So you can separate by this process of fractional distillation. You can separate this petroleum into the hydrocarbon components, taking advantage of the differences in boiling points among these different hydrocarbons. Remember, the boiling point increases with the length of the hydrocarbon chain. So taking advantage of this property, this boiling point, this differences in their boiling points, you can separate these hydrocarbons. You can read this on your own time, but also you can watch this YouTube video, which we can watch together right now to see how this is done. And related to that is also the process of cracking. And in cracking, it's a method for converting long chain hydrocarbons into shorter chain hydrocarbons. And this process is called cracking. For example, you can take this long hydrocarbon, crack it to get ethene and alkane, for example. And then also there's a YouTube video which we can watch together. There's 2 types of cracking that are very commonly used. One is proteolytic cracking, and the other one is catalytic cracking. And proteolytic cracking, you heat your mixture of your heavier petroleum your molecules. So the mixture is heated to very high temperatures, like about 700 degrees Celsius, and this causes the chains to break down into smaller hydrocarbon chains. In catalytic cracking, a catalyst, something that drives the reaction, drives the process of breaking this long hydrocarbon into smaller hydrocarbon. A catalyst speeds up the rate of the reaction without itself being used up in the reaction itself. So let's end our lesson in watching these 2 videos together. There's also a support question for you guys to look at. And then there is your key questions, your assignment associated with this lesson. And this is due this Sunday, October the 3rd. Okay. So please use the Dropbox when you're handing in these assignments. And I really encourage everyone to hand in every single assignment. Whatever you mark you get on it is certainly better than a 0 that you would receive by not handing anything in at all. And then you can also make use of advantage of those bonus assignments to improve your marks. If you have any low grades, then I can, if you've handed in bonus questions, then I can omit the lower grades and take your 16 highest grades of your assignments. Okay, so without further ado, let's take a look at fractional distillation. Here.
In this video, you will learn how fractional distillation separates crude oil into useful fractions. Crude oil is the term used to describe unprocessed oil. That is oil that has been taken directly out of the ground, either on land or under the sea. It is an exceptionally valuable resource. It provides us with a great number of hydrocarbons, some of which are useful as fuels, and others are used in the manufacture of many different chemicals and even plastics. However, in the raw form as crude oil, it can be a viscous, dark-coloured tar-like consistency, and the different fractions of hydrocarbons must be separated by fractional distillation for them to be useful. Before we understand how fractional distillation works, we should be clear that crude oil is a mixture of hydrocarbons with different chain lengths, some being short molecules and some being very long. Intermolecular forces act between molecules, and the longer the molecule, the greater the intermolecular force. As you can see here, the small molecules have weaker intermolecular forces, and so will require less energy to break them apart and turn them into a gas. They have a lower boiling point. The longer molecules have greater intermolecular forces. More energy is required. A higher temperature will be needed to evaporate these molecules. They have a higher boiling point. Now we understand how chain length is related to the boiling point of a molecule. Let us look at how this method works. As you can see, crude oil is heated up to a high temperature outside of the fractionating column. The hot crude oil, now mostly in vapor form, is pumped into the column. The column has a heat gradient and is very hot at the bottom, going cooler as we move up to the top. Even at the very bottom of the column, where the temperature is still high, some long chain molecules with high boiling points begin to condense back into a liquid. These are collected at the bottom of the column. The rest of the molecules start to rise up the column, making their way through bubble caps in each tray. The bubble caps slow down the rate of the rising vapor, and eventually the vapors get too cool, condense, and are collected as liquids in the trays.
Okay, so these are those bubble traps that they were talking about. And the whole process has to do with the difference, this temperature gradient, this being hotter at the bottom and getting cooler as you go up this fractionating column. So up here are cooler temperatures than down here. So then as these vapors are heated and they encounter these bubble traps, what they do is they condense. And you guys all know about the process of condensation. What does condensation mean? It means a matter is going from its gaseous state, from being in a gas state, and condensing to a liquid. So they hit these bubble traps here. It slows them down from rising. and the ones that get cooled condense and form into liquid and are removed, flow out of the column. They flow out of the column, and the rest of the gas that is still in the vapor form continues to rise until it meets the next level, where the hydrocarbon chains of the right size, based on their boiling point, the ones that are still have got a higher boiling point will again condense and cool down, while the ones with lower boiling points still continue to climb and go to the next level. So they're condensed and then they're collected in these collection trays. And the small molecules have lower boiling points, so they continue higher up, while the lower parts, the molecules with a higher boiling points are down here.
Small molecules have low boiling points and so condense much higher in the column where the temperature is cooler still. As you can see, hydrocarbons with similar boiling points are collected in the same tray, and this is why they are known as fractions. They are mixtures of hydrocarbons with similar boiling points. Each fraction has some important uses. Some examples of fractions are petrol, useful as a fuel for cars; naphtha, used in the manufacture of chemicals; kerosene as aircraft fuel; diesel oil, used as fuels for vans, cars and lorries; and bitumen, a mixture of large chain hydrocarbons used to lay roads. Now, at the end of this video, you should understand that crude oil is a mixture of important hydrocarbons, and that fractional distillation is the method used to separate crude oil into useful fractions with similar boiling point. You should understand that small chain molecules are collected at the top of the column since they have lower boiling points, and larger chain molecules are collected further down the column as these have higher boiling points.
Okay. And now let's look at cracking.
In this video, you will learn about the process of cracking, how it is carried out, and why it is done. From our video on fractional distillation, you should know that crude oil is a mixture of hydrocarbons with different carbon chain lengths. Smaller hydrocarbons have a lower boiling point and are more volatile, making them easy to ignite and more useful as fuels. Larger hydrocarbons have a higher boiling point, are harder to ignite, therefore not as useful as fuels. We use a lot of fuels in our day-to-day lives, driving cars, aeroplanes, lorries, and even heating our homes. This means there is a very high demand for small chain hydrocarbons. However, after fractional distillation, we find that we have a large supply of long chain molecules. The process of cracking breaks down long chain alkanes into a smaller alkane and alkene molecule. This allows the supply of short chain hydrocarbons to meet the demand for them, as the longer chain alkanes are broken down into shorter alkanes and an alkene. The alkenes are also useful as these can be used in the manufacture of plastics. Here is an equation showing that C12H26 is broken down into octane and butene. There isn't a set way that these molecules are broken down. In fact, C12H26 could also be broken down into decane and ethene, or even butene, pentane, and propene, as these equations show. The large hydrocarbon is broken down in quite a random way. Just note that in each equation, of course, since we had 12 carbon atoms and 26 hydrogens going into the reaction, the same must come out. The process of cracking is carried out in one of two ways, either by thermal cracking, using high temperature and pressure, or by catalytic cracking at low temperatures and pressures, but using a catalyst. In thermal cracking, the large hydrocarbons are heated to temperatures up to 750 degrees C and a high pressure of 70 atmospheres. This high temperature and pressure breaks the bonds between carbon atoms to make smaller molecules. Catalytic cracking is the method used mostly in industry today. The large hydrocarbons are heated to around 500 degrees C and are passed over a zeolite catalyst. The catalysts chosen tend to break the bonds in the large hydrocarbons and make molecules of between 5 to 10 carbons in chain length, making them very useful in petrol. Now, at the end of this video tutorial, you should know that cracking is the process in which large alkanes are turned into smaller alkanes and an alkene molecule, and that there are two types of cracking: thermal cracking using high temperature and pressure, and catalytic cracking, which is the method preferred in industry as it uses lower temperature and pressure and produces more molecules that are useful in petrol.
All right. All right, so feel free to watch those videos again as many times as you need to so that you can fully understand the process. Now, we have a few more minutes. I wonder if any of you have any specific questions about what we covered in today's lesson. If you don't have any questions,
No question.
no questions, okay.
Me too, I have no question, but if I do, I'll bother you tomorrow, miss.
Oh, no bother at all. No bother at all. Please go ahead and ask me your questions. I will do my best to get your answer to you in a timely fashion. So I guess I can maybe go and talk to you about some of the questions students from previous years have had that may come up for you too. So I just want to maybe show you this table here that indicates what do we mean when we talk about the different formulas and the different ways, excuse me, of representing these types of molecules. You could have the molecular formula, which just indicates how many carbons and how many hydrogens, okay? Or you could have the structural formula, like this one, that shows every single bond of hydrogen and carbon very clearly. So if I ask you on your test, on your midterm, to draw the structural formula, or if on your assignment it says, draw the structural formula, I mean, show me this. There's also the condensed formula, but if I say structural formula, I really mean this. I don't mean give me this or that, or even this. This is a line diagram. It's very useful. It's kind of a shorthand way of showing, okay, carbons and hydrogens, but as a student where you're just starting out and just learning about the structure of hydrocarbon chains, it's really too soon to be jumping into line diagrams so much. I would much rather see you give me the full structural formula. That way I understand that you understand and that you've learned the concepts. And also other ways of representing the molecules that you will encounter in this course. I might use slides or diagrams that show both ways, as I might resort to showing some line diagrams. Sometimes I might show these ball and stick models. This one is called a space filling model. You don't so much see the bond in between the atoms, rather you show it's a representation of the relative size, the relative radius of each atom and how they might be stuck together. So this is called a space filling model. And of course, the Lewis diagram, which I think you're all familiar with. So these are different ways of showing the exact same hydrocarbon molecule here. But the structural formula, when I ask for a structural formula, this is what I'm talking about, okay? I think somebody else at some point had a question about which one in this case would be the correct name for this molecule. If you were given a molecule like this, remember the parent chain is the longest chain. It's not necessarily the straight chain that is the parent chain. It could be the one that has some bends in it, that's fine, but that would be the longest chain. In this case, this would be incorrect, right? And this would be the correct name for this. Parent chain is the longest chain and it's not necessarily the straight chain. So just count and see which one gives you the longest chain. 1, 2, 3, 4, 5, as opposed to 1, 2, 3, 4. Yeah, this is definitely not the longest chain here. This is, okay. And what else? Okay, we went through this part. These are just some more tutorials on naming conventions. I'm not going to go through these one by one. These are actually all from your textbook. You can go, I will leave it in the lessons when I share this with you in your Google Drive. You can go through this on your own time, but perhaps this is something we might take up during our review, or if anybody has any specific questions. Next class, we can take up some of these naming and drawing examples for alkenes and alkynes. We did some of that here. So yeah, you can go through it, okay? All right, I think that brings us to the end of our lesson today. So next week, we will cover our next 2 lessons. Remember this assignment, you only have this one to do this week. So go ahead and spend some time trying out all of the questions and hand this in on time, please, by Sunday, October the 3rd. And I will see you next week. Get in touch with me if you have any questions. Okay, good night.
Good night. Have a good day.
Okay, open it.
Have a great
Good
night.
night.
Have a great night. Bye.